Okay, let's finish up chapter 1 here, section 1.6, inclusion-exclusion principle. It's something you've probably used if you've taken probability or done some minor set theory type stuff before. And as usual, we're going to take what is a fairly simple idea and complicate it severely. So okay, so we're working with a big set X, and it is going to be a finite set. So capital X, it's a finite set. All right. And what we're going to let is capital N of X is the cardinality of X. It's the number of elements in set X. Okay. And let's suppose that A and B are subsets of X. Okay. Now, we want to count the number of elements in the union of A and B. Okay. Well, we start by counting the number of elements of A, number of elements of B. Okay. Now, if A and B are disjoint, we're done. Okay, we just add the number of things in A plus the number of things in B, and that tells us the number of things in the union. But if A and B overlap, like I have illustrated over here with this Venn diagram, then you have to be a little bit careful, because if you count up everything that's in A and then add to it everything that's in B, okay, what you've done here is the stuff in the very middle gets counted once when you count the set A and once when you count the set B. So you don't want to count it twice. So the number in A, the union of A and B, it's a number in A plus the number in B minus the number in the intersection. Okay. And this is the simplest version of the inclusion-exclusion principle. Okay. So it's something that you can tell just by looking at the Venn diagram that makes why it makes sense. Okay, you just don't want to count anything twice. Now let's suppose we have 3 sets. Okay, now what's in the union of A, B, and C? Okay, let's start out like we did before. First, let's take everything that's in A, and you may not be able to read that. Add to that everything that's in B. Add to that everything that's in C. Okay, so we take the A stuff, the B stuff, and the C stuff. Okay, now like before, when we count things in A and count things in B, we've counted the stuff where they overlap twice. So we don't want to count that twice. So we'll subtract off the number of things in the intersection of A and B. When we count stuff set A and stuff in set C, we've counted the things where they overlap twice. So we need to subtract off the number of things that are in the intersection of A and C. And when we count B and C, we've counted count everything in B and count everything in C. Well, those elements that are in the intersection, we've counted twice, and we don't want that. So we'll subtract off the intersection of B and C. But think about this very middle spot down here. This is where everything overlaps. Okay. So the intersection of A, B, and C is included in A. So when we counted in A, we've counted it once. When we've counted B, we've counted this region twice. We've counted C, we've counted the region a third time. Okay. So when we subtract off A intersect B, we subtract it off once. So we subtract off those things in the intersection of A and C, we've subtracted off a second time. When we subtract off the number in the intersection of B and C, we subtract it off a third time. So we've counted it 3 times and we've subtracted it 3 times. So we really haven't counted it all. So we need to add it back in. Okay. Okay, now the book on page 60 goes through a precise derivation of this version of the inclusion and exclusion principle based on the 2-set version. You can certainly go through that. I think it's a little bit confusing when you're doing it that way. However, that's how it really ought to be done if you want to use the formula. Okay. Now this can be expanded to 4 sets, 5 sets, 6 sets, and so on. We just need a different way of writing it. Okay, so let's think about this a little bit. Now, if A is a subset of the big set X, okay. Oh, let me back up here. First off, we're going to let capital N stand for the number of objects in X. So rather than write this down, if I write capital N, it's everything that's in the box over here. Okay. Now, notice that if A is a subset of X, okay, then we define A prime. Okay, this is the complement. This is X minus A. And the number of things in A prime will be the number of total things in X minus the number of things in A. Okay. So I don't have a picture drawn here, but what we're talking about is a simple Venn diagram here. Okay. Here's my set A, and here's A, and everything is X. So the number of stuff out here in the complement of A is everything minus what's in A. Okay. Get rid of these guys here. Okay, now for 2 sets. Okay, let's recall De Morgan's laws, which says the complement of the union is the intersections of the complements. So what's not in the union, okay, which is this stuff out here. Whoops, I missed. Which is the stuff out here. It's the intersection, it's everything that's not in A and not in B. Okay. And if we count that up, the number of things that aren't in A and aren't in B at the same time, well, it's everything minus the number of things that are in the union of A and B. So the number of stuff that's outside is the whole set minus what's in the union. And this is the same thing as N minus, well, what did we have here? N of A plus N of B minus the number in the intersection. So the number of things that aren't in A and aren't in B are the total number of things in the set minus the number that are in A minus number that are in B plus the number that are in the intersection of A and B. Okay. Actually, I think I want to write it this way. N minus, okay. Oops, I'm so used to using lowercase letters here. Number of things that are in the intersection of A and B. So it's everything minus the number at A plus a number in B plus the number in the intersection. This is, our formulas are going to look like this in a bit. Okay. So for 3 sets, okay, things get a little bit awkward looking here, but so for 3 sets, the number of elements that aren't in A and aren't in B and aren't in C, that's the total number minus the number that's in the union. Okay. Which is, we'll go back to this formula we had before. So it is, tell you what, let's go down here. It is N minus the number in A minus the number in B minus the number in C plus the number in the intersection of A and B plus the number in the intersection of A and C plus the number in the intersection of back it up here. Number in the intersection of A and C plus the number in, I can't help but write lowercase a and C plus the number in the intersection of B and C. Okay. Then minus the number that are in the intersection of all 3 sets. Okay. Okay. So let me just rewrite this a little bit. We're going to come up with a more general formula here in a minute. But N minus, okay, these are all the singleton type sets. Plus the ones that are intersection of 2 sets minus the ones that are the intersection of 3 sets. Okay. So what we're finding here is we're finding how many are on the absolute outside. Okay. So we need to develop some notation here because we're going to have some general number of sets. So let's start with this here. Okay, so let's suppose A1, A2, A sub n are subsets of a finite set X, where capital N is the number of elements of X. Okay. Now here's where things get a little bit tricky. Let S sub 1 be the number of things in A1 plus the number of things in A2 plus the number of things up through AN. So it's a number of things that are in A1. Now these might be in some other set, but we're just looking at A1, counting up everything it's A1. Go to A2, count up everything it's at A2. Some of these might be in other sets. I'm not what I'm asking right now. And go to AN, count up everything it's in those. Okay. Now here's where it gets a little bit hard to write down. S2. S2 is going to be the number of elements of A1 intersected with A2 plus the number of elements of A1 intersected with A3 plus dot, dot, dot. And I'm leaving an awful lot out when I do all the dot, dot, dots. Plus the number of elements of AM intersected with AN. So in other words, what we're doing here, this is the sum of the number of elements that are found in all pairwise intersections of sets. So it's got A1, A2, A1, A3, A1, A4, and so on. A2, A3, A2, A4, and so on. A3, A4, A3, A5, and so on like that. Okay, now before I go on to the next thing, let's just ask a question. How many such pairwise intersections are there? Well, we've got n number of sets, and we're picking two of them. C, so n, choose two. Order doesn't matter, but they have to be different. Okay, that's going to turn out to be important in a minute when I do this great big long messy proof. Let's let S3, it's going to be number of things in A1 intersected with A2, intersected with A3, plus the number of things in, this is the number, it's the sum of the number of elements found in all intersections of 3 sets at a time. Okay, and we'll ask the same question. How many? Such intersections? Well, I've got n number of sets, and when I do one of these intersections, I'm picking 3 things out of it. So it's the number of ways of choosing, or a group of n, choosing 3 of them. Okay, and we keep this up. Okay. S sub n then is, well, there's only one thing in this. This is A1 intersected with A2 intersected with A sub n. Okay, it's a number of elements, and I'm using a small lowercase n. I shouldn't be. Okay, it should be an uppercase n. It's a number of things you get when you intersect all of them. And over here, How many different sets are there? Well, there's C of N. I'm sorry, I'm leaving things out. I've got notes here and I really ought to refer to them. Okay. All right. S sub R. It's an R, not an N. It's a number of things in the different intersects R number of sets. So it'd be A1 intersected with A2 up to intersect A sub R, and then all possible combinations of those sorts of things. And again, how many of them are there? There's N sets, and we're picking R of them to be intersected. So this is a number of different terms we're adding here. Okay. And finally, to keep this up, S sub N here is just the number of things in the intersection of all of these sets. A1 intersected with A2, the intersection of that with everything. Okay. All right. Now we're ready. The inclusion-exclusion principle says the number of elements that aren't in A1 and aren't in A2 and so on and so on and aren't in A sub N. It's a number of elements in X minus those elements, the number of elements that you've counted when you do one set at a time. Okay, plus the number of elements you counted when you do two sets at a time, minus the number for three sets at a time, and so on and so on. The last term is minus 1 to the n times S sub n. So it's an alternating sum. Okay. And let me see if I can give a little bit of a proof of this. It's kind of a interesting proof here. And one of the things, before I do the proof, I need to go off to the side and do something else, I believe, here. Okay. So, tell you what, let's insert a blank page. Okay. What happens when you take, say, x plus y to the nth and you expand this? Well, you'll get x to the n, then you get n, x to the n minus 1 times y. Plus, what are these coefficients? These coefficients are the combinations. Okay, C of n choose R are binomial coefficients. Okay. All right. So I'm going to use that at some point here, that when you're talking about adding up a bunch of these C sub R's, these are the binomial coefficients. The expansion of x plus y to the n is the typical coefficient there is C of n choose R, or n choose R. Okay. Okay. So let's go back to our proof here. What I'm going to do is, to do this proof, we need to we need to show that if X is in this, then its total count on the right-hand side, you can't read this, is 1. And then if X is not in this, its total count on the right is 0. Okay. Okay. So let's suppose that X is not in so X is in this intersection. So that means X is not in any of these sets. Okay, so it's not in A1 and it's not in A2 and so on. Okay, now X is in N. X is in X, but okay. So we look at the right-hand side, it's counted once here. In this number, but since it's not in any of the A's, in none of the S's, so it's counted once on the left and once on the right. Okay, so that much is fine. Now, if it's in this set and you would count it on this side, the only place it's going to be is over here. So it'd be counted once on the left and once on the right. Now, let's suppose X is in a single one of these A sub i's. Okay. Then X is not in the intersection of all these complements. Okay, so it's not counted on the left. So as far as X is concerned, the left side is 0. Now, if it's in a single A sub I, it will show up, it will be counted once in N. Okay, excuse me. On the right, it's counted once in N. Okay. And once in N sub AI, okay, once in, which is in this guy. So what we have on the left is 0. On the right, we have it's counted once in N and once in the S1 and nowhere else. So we get it's not counted on the left, and it's counted once but subtracted off, so it's 0 on the right as well. Okay. So now comes the tricky part, is looking at the general case here. So now let us suppose okay. That X is in R number of these N number of sets. Okay. Okay. So let me write everything down here. We have the left-hand side okay, of the sets 1 through N. We have capital N, then we have minus S1 plus S2 minus S3 plus dot 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 plus, okay. And at some point there's R here, so it's minus 1 to the R S sub R plus dot 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 up to the very last one, minus 1 to the N S sub N. Okay, so where do we count X? Okay. So it's in our number of sets, so that means X is counted. Okay, so over here it's 0. Okay, so it doesn't show up there. It's counted once here, once here, once, no, excuse me. I'm not saying this right. So X in this set, this set, this set, this set, this set, but not here, because I'm not saying this very well at all. I'm saying it right, I'm just not writing it very well at all. Okay. X is not over here. Okay. It is here. It is here. It is here. It is here. It is up to here. Now, from the rest of the way over here, these are intersections of R plus 1 or more sets. X is not in R plus 1 of these sets. It's only in R of these sets. So it's not there. Okay, so let's count then. Okay, X is counted, oh yeah, there's one set here. How many sets are there for S1? Okay. Well, there's, okay, there, it's in R number of sets. So here, it's in R number of these. Okay. This counts up the intersection of all the two sets at a time. Now, X is in R number of these sets, so it's in R choose 2 of these. It's counted R choose 2 times here. Okay, this is the S3 is the intersection of 3 sets at a time. X is in R number of those sets, so the 3 intersection ones, it's in C of R choose 3. Okay, and down here In this set, S minus 1 to the n, S sub r, minus 1 to the r, S sub r. Okay. R number of the sets contain S. So of those R sets, there's only one way to pick R of them. And of course, it's all 0 from there on. Okay, I'm not sure I'm making sense here, but we're going to go with it anyway. S2 is the set of all, it's how many elements there are when you intersect all pairs of the A's. R number of those A's contain X. So this is the number of times X is counted there. S3 is the number of elements when you intersect, you add up the number of elements in the intersections of 3 sets at a time from this group of A's, these n number of A's. Now, R of those sets contain X. So R choose 3 is the number of different ways of getting 3 sets from this group of R that contain X. So that's how many times X is counted there. So let me write all this down here. So what is this? This is 1 minus C of R1 plus C of R2 minus C of R3 plus dot, 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 plus, and the coefficient out in front of this one is minus 1 to the R, C of R. But now wait a minute, something's going on here. This has to do with, this is C of N1, no, C of N0, C of N1, so on. These are binomial coefficients here. So this is actually, here's where you're going to have to think about it a bunch. This is actually what you get when you take 1 minus 1 to the R power and expand it. All right, and anyway, this is 0 to the R, so this is 0. So it works, okay? When you start going through here and counting up, it doesn't appear there. So it's not in here. Okay, so its count on the left side would be 0, the count on the right side would be 0 as well. This establishes that theorem. Okay. Strange proof. It's a good theorem, but it's a strange proof. Let's work an example here. And this is example 1.6.3. Let X be the numbers, the positive integers from 1 to 600. In this set, how many positive integers are not divisible by 3 or 5 or 7? So not divisible by any of those 3 things. Okay. So we're going to set this up. We're going to let A be the numbers not divisible, the numbers divisible by B. B, the numbers divisible by 5, and C, the numbers divisible by 7. And what we're trying to find is the number of numbers in this set that aren't divisible by 3 and aren't divisible by 5, aren't divisible by 3, and aren't divisible by 5, and aren't divisible by 7. Okay, so we need to count some things here. First, how many things are in this set? Okay, well, there's 600 numbers in the set, and every third one is going to be divisible by 3. 600 over 3 is 200. How many elements in this set are divisible by 5? Well, that's 600 over 5 is 120. Now, how many in this set are divisible by 7? Well, if you take 600 over 7, you get 85 and 5/7. Okay, well, that's not quite right. What we're really doing is we're taking the floor here. In other words, there are 85 multiples of 7 in this group. Now, these guys, I really should be taking the floor here as well. But they worked out evenly because 600 was divisible by 3 and 5, but 600 not divisible by 7. So he goes 85 multiples of 7 with some numbers left over. Okay. All right, now let's continue with this. Now, I want to know how many things in this set are divisible by 3 and 5. Okay. This would be the numbers that are divisible by 3 times 5, or 15. And that's going to be 600 over 15, which is 40. Okay. I don't have to round down, okay, but I mean, what we're really doing is we're how many times does 15 go into 600 evenly? Okay, and throwing the remainder away. The number in the intersection of A and C. This would be the number divisible by 21. So how many times does 21 go into 600 evenly? Well, that's the floor here. 21 divided by 600 is 28 point something. It goes in 28 times. Okay. One more of the two set intersections, and these would be the things in B intersected with C. So this is the number divisible by 5 times 7, 35. So you take 600 divided by 35. Okay. And that's going to be 17 point something. So 35 goes into 600 evenly 17 times. And now finally, we take the number that are in all three sets at the same time. And that's the number divisible by 3 times 5 times 7, which is 105. So take 600 divided by 105. Okay, it doesn't go into it evenly. Okay, but this is 5. It goes into it 5 times completely. There's a remainder left over. I'll get it right one of these days. This is really hard to do. I want my 5s to look very good. We'll do it this way. That'll fix that. Okay. Well, now let's set up our equation, or set up our computation. I think it's pretty straightforward. We are working in blue, yes. It's n minus, okay, these are all the numbers for the one element sets. Excuse me. Start this up. I should have said this. You add all these up, you get S1. 200 and 120 and 85 is 405. Add all of these up, you get S2. 40 plus 28 plus 17 is 85. And this is S3. So the number n that's not in A and not in B and not in C is n minus S1 plus S2 minus S3 equals 600 minus 405 plus 85 minus 5 is 275. Okay. Now, what I'm going to do next is work a really, really long problem. Now, I had in mind, we're going to skip some of the stuff in this section. I'm going to look at the phi function, and we're going to skip that. We're going to skip on over. I want to do, what had in mind to do example 1.6 plus 0.6. Okay. And I'll read it out for you. Find the number of solution in the integers of the equation a plus b plus c equals 25, where a is at least 2 and most 4, b is at least 3 and most 6, c is at least 4 and at most 8. Okay, so a is at most 4, b is at most 6, and c is at most 8. This is a really long problem, but think about that. If the largest a can ever be is 4, the largest b can ever be is 6, the largest c can ever be is 8, then 4 plus 6 plus 8 is 18. You're never going to have numbers that add up to 25. Okay. So when I worked this out, I said, wait a minute, I got 2 pages of solution on here, and said, stupid. Anybody who looked at it and thought about it halfway would see there is no solution, or there are no integers. Okay. So I rewrote the problem a little bit to think of it this way. Find the number of integer solutions to p plus q plus r equals 25, where p is between 2 and 7, q is between 3 and 9, and r is between 4 and 11. So there will be some solutions because p can get up to 7, q to 9, and r 11, and that's 27. So certainly, okay, these things range from 2 plus 3 plus 4, 9, up to 27 when you add them up. So there will be some in here that add up to 25. So how many different solutions are there to that? Okay, now you can find them if you want to. What we'll be doing is we'll be using this result that we did a theorem 1.4.2a that we had a while back. And it said the number of distinct non-negative integer solutions to this sort of linear equation, where we have 3, okay, we have n number of variables, and r is the, well, I shouldn't have used p, q, and r here, but r is this guy here, the sum, okay, is c of r plus n minus 1, n minus 1. So in this case, n equals 3 and r 25. Okay, so what we should have, okay, now I can't just use this now, excuse me, actually I can't use this, period. Okay. problem is this is non-negative solutions, and these guys, well, non-negative means greater than or equal to 0. So the first thing I'm going to do is shift everything so that each of the variables becomes greater than or equal to 0. Okay, so let's we'll do it this way. P is going to be, P equals x plus 2. So this means that x is between 0 and 5. Okay. Q is going to be y plus 3. So when you subtract 3 from both of these, 0 less than or equal to y less than or equal to 6. And R is going to be z plus 4. I'll be getting that from here. So that okay, we subtract 4, you get that the z is between this and 7. Now, when you put these things into our equation here, P is x plus 2, R is y plus 3, Z is, Q is y plus 3, R is z plus 4, equals 25. Subtract off the 2 and 3 and the 4. Okay, we have x plus y plus z equals 5, 9, 16. Okay. So this is the equation we're working with here. We're looking at non-negative integer solutions to this guy. Okay, so we want x plus y plus z equals 16 with certain restrictions. X is less than or equal to 5, z is less than or equal to 6, y is less than or equal to 6, and z is less than or equal to 7. Okay. Now, if I didn't have these upper restrictions, in other words, if I was just looking for all the non-negative integer solutions to this equation, then 1.4.2a says this would be C of, okay, R is this number over here, so 16 plus n is 3 minus 1, 3 minus 1. This is the number of ways of picking, from 18, picking 2 things. And I've got a number for that somewhere. Well, I'll get that in a minute. Okay, but I do have some restrictions. So what we're going to do, this is going to be my capital number N, and we're going to throw out solutions where x is greater than or equal to 6, or y is greater than or equal to 7, or z is greater than or equal to 8. Okay, because if I throw out solutions where that happens, I'll have this solution here. Okay, this is going to take a while. All right. Okay, so first let's look at, so keep this in mind for N. First, let's look at our first set A. is is where the x's are greater than or equal to 6, but we don't worry about x or y. But okay, if you remember, we're just looking at x greater than or equal to 6. Okay, if you go back and remember how you did this, is you redefined x to be, you put it like a slack, x prime plus 6. Okay, so that you'd have x prime plus 6 plus y plus z equals 16. So you'd be looking for solutions x prime plus y plus z equals 10. Okay. So this has c of 10. This is my r, plus still 3 variables. So this is 12 comma 2. Choose 2 number of solutions. Okay. Okay, now let's look at the ones where y is greater than or equal to 7. So we'll redefine y as being some y prime plus 7. Okay. So we'd have x plus y prime plus 7 plus z equals 16. So we're looking at solving x plus y prime plus z equals 9. Okay. And this has c of 9 plus 3 minus 1, 3 minus 1 equals c of 11, 2, so number of solutions. Okay. And the c, we're going to look at the case when our z's are greater than or equal to 8. Okay, that's what we want to throw out. Okay. And in that case, again, the way you work this problem is you redefine your z as something plus 8. So you'll have x plus y plus some z prime plus 8 will be 16. So that's supposed to be an 8 there. So if you subtract that, we're looking at a solution to x plus y plus z prime equals, so 16 minus 8 equals 8. And this has c of 8 plus 3 minus 1, 3 minus 1 equals c of 10, 2. Okay, now those are all add these up, that's S1. Okay. Now I've got to do the S2s, which constitute 2 of these things happening at a time. So I want to throw out A intersect B's. So we'll go here. This is what we've got here for those 2. So it's going to be x is x prime plus 6, y is y prime plus 7, and that's equal to 16. So when you subtract your 13, 6 and 7 is 13, you get x. You get prime plus y prime plus z equals 3. And that has c of 3 plus 3 minus 1, 3 minus 1 equals c of 5, 2, number of solutions. A intersects C, then that means we have an x and a z that need to be worked with. It's because x is going to be greater than or equal to 6, and z is going to be greater than or equal to 8. So that will be x prime plus 6, and the y's we're not worried about here, and z prime plus 8 equals 16. So we have x prime plus y plus z prime will be 16 minus 14 will be 2. Okay. Remember, these things are non-negative, so we do have some, these might be 0 here. So this corresponds to C of 2 plus 3 minus 1. 3 minus 1 equals C of 4 comma 2. And then we have B and C. So we want to throw out the solutions where y is greater than or equal to 7 and z is greater than or equal to 8. Okay. So in this case, x I'm not worried about. Okay. And when you do this, you're going to have x plus y prime plus z prime equals 16 minus 15 is 1. The number of ways of doing that is C of 1 plus 3 minus 1, 3 minus 1, C of, in other words, 3 comma 2. These add up to my S2s. Excuse me. All right. And finally, we have to look at what happens if all three of these numbers are over the limit. So it's going to be x prime plus 6 plus y prime plus 7 plus z prime plus 8 equals 16. X prime plus y prime plus z prime, this is supposed to be 16, is 16 minus 21, okay, and this has no solutions. Remember, we're looking for non-negative numbers, so S3 equals 0. Okay, so our final answer is, let's see if I've got this down here. Okay, now the number of things that where x is not greater than or equal to 6, and y is not greater than or equal to 7, and z is not greater than or equal to 8, is the total number of everything, which we got way back up here somewhere, C of 18, 2. Okay, and now I subtract off all of this, the S1 stuff. Okay, make sure I got that right too, okay. Then I add in all the S2 stuff because it's an alternating sum. And then I subtract off the S3 stuff, which is 0. And magically, when you get this, the number is 6. So the total number of non-negative solutions to this equation where one variable's between 2 and 7, the other's between 3 and 9, and the third's between 4 and 11 is 6. Okay. Well, frankly, you probably could have figured them all out by now, going through the proof. Okay. One more idea here, if I can find my notes. We're going to be doing it without any sort of proof. So it's a definition. A derangement derangement, let me spell this right. Let's see if I can perform some magic here. Okay, well, sort of. We've done arrangements. This is a derangement. Okay. Of n objects x1 up to x2 up to xn is an arrangement of these objects so that no object appears in its original position. Okay, so particular, if I had A, B, C, D, then A, C, B, D, excuse me, have A, B, C, D, then A, C, D, B is not a derangement. Okay, but B, A, D, C is. A is not in A's position, B is not in B's, C is not in C's, and D is not in D's. Okay, so we count them. And this is theorem 1.6.3. The number of derangements of a set of n objects is, okay, we'll use d sub n here, n factorial times 1 minus 1 over 1 factorial plus 1 over 2 factorial minus 1 over 3 factorial plus dot, 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 plus minus 1 to the n times 1 over n factorial. Okay. So the only example I'm going to do here is if we have our set X be the four elements A, B, C, D, where A, B, C, D is the original position here, then the number of derangements is 4 factorial times 1 minus 1 over 1 factorial plus 1 over 2 factorial, oops, minus 1 over 3 factorial plus 1 over 4 factorial. Okay, this is 24 times 1 minus 1 minus 1 half, excuse me, plus 1 half minus 1 sixth plus 1 24th equals 9. There's 9 ways of arranging these, and there's 24 ways of arranging these, but 9 of them are deranged. Okay, that ends section 1.6, and that ends the chapter on combinatorics. It really hasn't covered a lot of pages, but there's a whole lot in there. I hope you have enjoyed this. And I hope you think that there's something useful here. Counting is a very useful thing in mathematics. Being able to count stuff. Okay.